efficient. Okay, so we're going to talk about an application, a real-life application of quadratic equations. Quadratic equations, those are parabolas, either this way or this way. And so the whole idea is, how are they useful? How can we use them? And there's an awesome formula called the vertical motion model. And that formula is that formula right there. And it looks scary. I mean, I would imagine, for many of you, you think, oh my God, negative 16 in front of that thing, right? But it's not as scary as it looks. And the beauty of this, I'm going to first talk about what each letter stands for, okay? So you have to make sure you have that written down. And then your H here is the height at any point during the curve, okay? So if you had a curve, if I had a curve here, right? Wouldn't you agree with me that it's a sad face parabola? Yeah. Right? Because think about it, what's a quadratic equation? What's the basic formula? Y equals
A plus
ax squared plus bx plus c, right? That is a quadratic equation. You've got this x squared, t squared, x, c, and s. The a is negative 16, the b is a v right now. And that we use different letters so that we know what they stand for. And it just is going to help, right? It's going to help us define it. So the h is any time, the amount, whatever, the height of the ball at any point along this curve. Does that make sense? Mm-hmm. It's the height at any point, all right? Based on time, okay? Height at any point on parabola. Okay? And your t is and the height, by the way, is in feet. Okay? When you use negative 16, it's based on feet. There's a different formula if you're going to use meters, right? What?
When you put positive 16?
It's got to be negative. Because, because a positive would mean like throwing a ball and it would look like this.
Awesome.
You can't, it would be awesome, I agree, but it doesn't work, right? I mean, it works if you're throwing it underwater and it's got a little air in it and it pops up again.
Wait, how do you do that?
But
you
anyways,
do that?
I don't know.
Yeah, you've never done that?
All right,
Hold
T.
on, guys.
So T is equal to time.
You can do that.
Guys, T is equal to time in seconds, right? So we're talking feet and seconds. That's what we're talking about. Time is seconds, height is feet, right? And so V
Velocity?
V stands for, yes, exactly, velocity, but it stands actually for initial vertical velocity. In other words, if I throw something, everybody look at me for a second. When I throw a football, Maddie, look. If I throw a football, wouldn't you agree with me that there's a vertical motion, right? Even though I'm throwing it over there, there is a vertical motion. It's going up, right? I'm not just dropping it like that. I'm not just dropping. Is there any vertical motion here?
Yes.
No. Well, not initial. There wasn't any initial going up or initial going down. It was just steady. Does that make sense?
Wait, what? No, because...
So if I'm just dropping, that's got an initial
so
positive.
That moment before it gets thrown
But also,
or dropped, right?
why is that
The
not
very
initial?
moment that it's dropped, that very moment, if there's a force going upward,
Well, why
that's
does it
called a
go upwards?
initial vertical
If I
velocity.
throw it downwards.
That's also called an initial vertical velocity.
But
What
he's
if I
not
go like
throwing
this?
it.
But it's going to be a negative velocity. This is a positive velocity. Throwing it down is
Except-
going to be.
What if dropping it? Is that out?
That's what I just said. So dropping it, there is no initial vertical velocity, upward or downward, there's no extra force being imposed on this. I'm just dropping it. So V is 0 when I just drop it. Does that make sense?
Yeah.
Yeah. Okay.
What did I just say, Zane? V is 0 when I just drop it, right? It's 0. Therefore, if I'm dropping something, I no longer have the VT, because V is 0. V times T is 0. Right? Yes.
So, Gary, would that make it possible for a parabola to be a straight line?
Ah,
If I throw it up like that, it stays in a straight.
very good question. Okay,
Like
think
a
about it.
skinny ass parabola.
Yes, because that's what
Just
you
like-
would think. That's a great question, Maddie. That's a really great question. But look,
The old parabola.
look at this. Let's say I'm on the y-axis, right? And let's say I'm up here, right? And I'm like 50 feet above the ground. And I drop this thing. You'd think it would go straight down like this, right? On the graph. But the graph is a twofold graph. We've got up and down is your height, right? Up and down is your height. And to the right is your time. So even though, yes, when you drop it, it goes straight down, the parabola that is created based on time, as soon as it drops, the clock starts ticking, right? So suddenly, you've got a parabola.
Wait, why?
Does that make sense? You see what I mean?
No, that doesn't make any sense.
Yes, it does.
Why does the
So
parabola-
as soon as it drops and the time is moving, the time starts, the clock starts ticking.
Okay, yeah.
So
That
then
part I
I'm modeling time and height at the same time.
Right.
So it creates a parabola versus
I
a
get
straight drop. Yes.
How does that? Right, I get what he's doing. I'm just saying, why aren't we trying to calculate where it's gonna reach?
Now we're trying to calculate how long it's in the air.
Oh, then never mind. Because I thought you were trying to calculate where on the ground it was gonna hit.
No, I'm calculating
Then
how
that makes
long
sense.
it's going to take. So that's the idea, is where will it hit? I mean, where will it hit the 0 point? When will this H become 0? Right? That's finding the zeros.
Okay, so
Which you
the
guys already know how to
object
do.
isn't where.
It's not where it hits; it's how long it takes to hit. That's
so
the object.
That makes sense.
So we're not, okay, so I thought I was under the impression that we were trying to, that parabola was supposed to measure the physical, thing of going up and then down. But time is like, so it's basically like,
Well, we will eventually. Right now, there are. This formula works for this. It works for, this, and it
Whoa.
works for this.
Yeah.
It works for all of these. Okay.
Okay, so this
And
is-
so, but what I'm doing is I'm taking out this middle factor, because I know you guys know how to solve these, right? I don't want to make it too hard for you, right yet. But if we get rid of the initial vertical velocity, there's no upward movement, and there's no forced down movement, initial forced movement. It just drops, right? Everything tonight on the homework is just dropping. So if it's just dropping, meaning there's no initial vertical velocity, this is your formula.
Oh, it's
did my
just
homework.
16 t squared
H
plus s.
is equal to negative 16t squared plus s. That's the formula we're going to be using tonight.
V
Right?
times
Because
0
V
times
is 0.
T is equal to
Right,
0.
exactly.
I'm so smart, Gary.
You are smart.
Thank you.
Now, the last thing I didn't say is S. What does S stand
Seconds.
for? It's the starting height.
Yeah, I'm at
Starting height. S stands for the starting height. Okay, so up here, if I started at 50, and I just dropped it, meaning there's no initial vertical velocity, I just dropped it, my formula would be H is equal to negative 16t squared plus 50. Right? If I'm on top of the Empire State Building and say it's 2,000 feet high, it would be H equals negative 16t squared plus 2,000. If I'm on top of this table and I drop something, it's H is negative 16t squared plus 3.
So,
3 feet, say, or something.
are we?
Okay, so now let's quickly look at this. Let's look at this problem.
I have another question.
Yes, go ahead.
Are we calculating how it accelerates?
you're calculating only the amount of time it takes for this. The
Right,
minute
but
I let
do
go
we have
of
to
this.
calculate how much it accelerates?
No.
But then we're not getting.
So basically in physics, scientists, right? Scientists will look at real life situations and they will try to model those situations with an equation. They try to find an equation
Does this
that works.
calculate speed?
And this calculates, this takes into consideration gravity, right? Because gravity is what is affecting this drop, right?
But it doesn't calculate the speed at which it accelerates because, like,
Correct.
if it's like falling at one
Well, it
meter
sort of
per
does.
second, or
It
like
sort of does.
1 foot per second, like it would.
It's going to go faster and faster and faster and faster, right? So it does. It's taking that into consideration. Basically, it's the negative 16 is what's actually creating that. We're modeling what's happening in real life with an equation that is fairly accurate. Okay, does that make sense? So let's look at this. Fenway Park. It's a Major League Baseball park in Boston. It has seats on top of the left field wall, sitting right on top of the wall. And this guy sitting on one of those seats drops his sunglasses. He is sitting 38 feet above the ground, right? The height H, right, in feet can be modeled by the function H equals negative 16 t squared plus the starting height, 38, right? Pretty straightforward, right? Okay, and then it says where t is the time in seconds after the sunglasses were dropped. Find the time it takes for the sunglasses to reach the ground. So here we go. We have this equation, h equals negative 16 t squared plus 38. And they're asking us to find the time when it hits the ground. What is the height, this height, when it hits the ground? Jackson, what is the height of this when it hits the ground? What's h? Do you agree with him? This is the height. So Jackson, if we're up here, right, and it falls down, the height is any place on this amount, whatever. If time was here, the height would be here. If time was here, the height would be here. If time was here, it was here. But as soon as it hits the ground, h, the height, would be 0. That means we're setting this equal to 0. We're finding the zeros. What you guys have been working on for a month now, right? Finding the zeros. Does that make sense? You're finding where it crosses the x-axis. Finding the zeros is finding x when y is 0. So we're going to make that 0. So now, since we know we want to know time when h is 0, we just do this. 0 equals negative 16 t squared plus 38. Now what do I do? Now we're doing problems you did last week.
Solve for t.
Solve for t. How do I do it?
Okay, add 16 t squared.
Yeah, I don't like that negative in front of the t squared. I'd rather it be positive. So let's just add that. 16t squared to both sides.
Then you have.
Hang on, let me get there first. Let me catch up. 16t squared is equal to 38. Now what?
To 5 by 16.
Yeah, I don't want that 16 in front of the t either, right? I want to say just t equals. So I got to get rid of the 16, divide both sides by 16, get out my calculator. Uh-oh. Where's my calculators?
Got him. I caught them.
Oh, great, great.
So 38 divided by 16, is that what we're doing?
Yep.
2.375.
Thank you.
T squared is equal to 2.375?
Yeah.
Okay, now what do I do?
Square root it,
Square root it.
and that's 1.541.
So t, time, is equal to plus or minus
1.541.
541 seconds.
About.
Okay, approximately, right? Approximately,
No, that's exact.
plus or minus 1.541 seconds. So it will, his sunglasses, now the question is, there's two answers. There's negative 1.54 seconds or positive 1.54 seconds. Which one is more likely to be the right answer?
Positive.
Positive, right? That's an example of where You've got to use logic to figure
It's
out.
not like Inception where like
And-
he turns the world
Right,
around and then he like
exactly.
drops his sunglasses
Right.
in reverse onto the
You got it.
guy's head. That'd be
So
cool. They should have that
time-
in Inception too.
So it took approximately 1.541 seconds for the sunglasses to hit the ground. Okay, does that make sense? Questions? Answers? Everybody got it? I wonder if we should do,
I have a question.
I wonder if I should just give them the homework to work on now, and then we'll go out, we'll have a thing in class, we'll go outside tomorrow, and we'll just use the period to, we're gonna, I think that would be fun, because I'd like to spend some time outside. We're gonna try dropping a stone or something from different heights outside, like the treehouse, right? We're gonna go up the treehouse, get as high as we can, we're gonna measure the height, and then we're gonna calculate how long it's gonna take for it to hit the ground, and then when it hits the ground, we're gonna time it with a timer. I've got these timers, so half of you guys will have the timer. Yeah.
For extra credit, can we calculate how much pain would come if you dropped it on his head?
Yes, you may.
Great.
It would
knock
somebody out.
How much pain
Wait, that-
your knee would be in if you landed on Jake's thigh, right?
It wouldn't be that painful.
Or yeah, it was last week. Okay, so that's it. So I think
That was me.
that's it on the
Yeah, that was
lecture.
it. That was it, not me.
That was me.
I got no damage.